Hello, this is Dr. Joe Trout from the physics program at Stockton University. Today we're going to talk about chapter 1 and talk mainly about units and measurements. So when we measure things, we need to have units, and the unit for length is a meter, and the unit for time is a second, and the unit for mass is the kilogram. And these have been defined by different methods through the years. The first definition of a meter, for instance, was 1/10,000,000th the distance from the equator to either pole. This was a hard to reproduce measurement, as you can imagine. And then there was a platinum iridium rod that was kept in a special vault with 2 scratch marks on either end, and that defined a meter. And in 1983, it was defined as the distance light travels in a portion of a second. For the second, it was once defined as a portion of a mean solar day, and now it's defined by the oscillations of a cesium atom. For a really long time, till a few years ago, the mass was actually defined as just a chunk of platinum iridium that sat in a special vault. And here shows a little bit of the history of a meter and how it was defined. For the English units, the units are foot, slug, and second. And 1 foot is about 1/3 of a meter. And 1 meter is a little more than 3 feet. So a little more than a yard. A slug, which hardly anybody ever uses this unit, is about 14.59 kilograms. And a kilogram is about 0.068 or 69 of a slug. We're going to define something called a scalar and something called a vector. A scalar is something that just has magnitude. So for example, mass is a scalar and it has just magnitude, not direction. Weight, on the other hand, is a vector, and it's a measure of force. A force is a push or a pull, and it has both a magnitude, so how strong the force is, and a direction, the direction in which the force is acting. So for mass, we said the unit are kilogram and slug, and for weight, the units are newtons and pounds. The problem is that our mass is constant everywhere in the universe, unless we start moving at extremely high speeds that we'll talk about in a couple of chapters. However, our weight will depend on what planet we're closest to. So on Earth, our weight is defined by the mass times the acceleration due to gravity on Earth, which is about 9.8 meters per second squared. We'll talk more about this on the chapter on forces, but for now, realize that mass and weight are 2 different things, and your mass will remain the same throughout the universe, and your weight will change depending on which large planet or which planet you're closest to. These units have prefixes, and they go from everywhere from iota, which is 10 to the 24th, to yocto, which is 10 to the negative 24th. Some of these might look really familiar. For instance, the kilo for kilometer and kilogram, and the centi and milli for centimeters and millimeters. And some of them are less used. So for example, yotto and alto and zeppo and yocto I've not used very much. And hecto and deca and deca and deci are also not used very often. In this class, we'll use mostly these, right? The kilo for things like kilometer and kilogram, centi and milli and micro for centimeters and millimeters and micrometers, and we'll use it for time, for instance, milliseconds and microseconds. Nano and pico and femto are used a lot in electronics, right? So we use them for things like capacitors are measured in pico and femtofarads. The larger ones here, such as zeta and exa and peta, are used a lot in computer science, right? So our storage on computers is getting larger and larger, and we're starting to reach those limits. So a kilogram is 1,000 grams, or 1 times 10 to the third grams. A centimeter is 0.01 meters, or 1/100th of a meter, and we can go on. So here shows some convenient or some commonly used conversions. So 1 mile is about sorry, that's a typo. 1 mile is 1.609 kilometers, or 1,609 meters. So ignore this period here. And a kilometer is about 0.6 miles, and an hour is 3,600 seconds. And we also have units that you're probably less familiar with. So if we look at the pressure of the atmosphere, it's about 14.7 pounds per inches squared. But other popular units are the atmosphere and 1.015, 1.013 times 10 to the 5th pascals, or 76 centimeters of mercury, or 30 inches of mercury. These all mean the same thing. When we make conversion factors, what we do is divide one by the other. So for instance, if we have 1 mile equals 1.609 kilometers, and we divide both sides by 1.609 kilometers, we find out that this conversion factor is equal to 1. And that's convenient. That means we can multiply any number by this conversion factor, and we won't change the number. So for instance, if you'd like to run, you probably know that 5 kilometers is equal to 3.11 miles, right? And how we came up with that is that we know that 1 mile equals 1.609 kilometers. So we can put the mile in the numerator and 1.609 in the kilometers in the denominator. The kilometers will cancel out, and 5 divided by 1.609 comes out to be about 3.11 miles. If we also measure speeds, and for instance, 20 meters per second, is that fast? Well, we can convert it into miles per hour and see what we think, right? So to get rid of the meters, we know 1 mile is 1,609 meters, and the meters will cancel out. And 1 hour is 3,600 seconds, and the seconds will cancel out. So 20 meters per second is about 44.75 miles per hour. So in class, we're going to keep everything to 2 decimal places, right? So we have to take the calculation. You can just round to 2 decimal places, okay? And we'll talk more about why this is important later. For now, let's assume that everything we do in class or on the chalkboard, we use things with precision that is down to 2 decimal places. So if we wanted to convert 60 miles per hour to meters per second, we can multiply it by this conversion factor, 1,609 meters divided by 1 mile, so the miles will cancel out, and 1 hour in the numerator and 3,600 seconds in the denominator, and the hours will cancel out, and we end up with about 26.82 meters per second. Wanted to stop for a second and once again define scalar. Scalar has magnitude only, and scalar, some examples of scalars are mass and distance and speed. Excuse me. For the vector, we have magnitude and direction, and some examples are displacement, velocity, acceleration, and force. So if we talk about the distance, that's a scalar and has only magnitude of the total distance traveled. Right, so it's the length of the total distance traveled. The displacement is a vector, and it's the distance between the final position and the initial position and the direction, and it points from the initial position to the final position. So when you go in lab, we're going to make measurements, and we'll generally have some uncertainty or error, right? So really, we should call it the uncertainty, not the error. And there's two types. The first type is systematic. So in this case, each error that we have in a measurement, if we're making multiple measurements, have the same sign. So here's an example. Let's say you use a meter stick to measure the length of the room. So you probably have to use the meter stick several times. And let's say that that's an old meter stick and it's been worn down by a millimeter. Right? So if you measure something using the whole meter stick, what will happen is that your measurement that you make will be longer than the actual distance. So each time you measure, you'll be off by a millimeter. And you'll actually be measuring, your measurement will be longer than the actual measurement. There's also random error or uncertainty. And these are chance variations in a measurement. So these errors are avoidable, right? So they are just likely to be positive as negative. And these errors can be minimized by taking many measurements and averaging together. So for instance, let's say we had the whole class measure the length of the room. Some people's measurement will be too long, some people's measurement will be too short, and some people's measurements will be just right. And we found that they're pretty much random. So if everybody measures the room, and then we take an average of those measurements, all the ones that are too large will cancel out with the ones that are too small. So if we take enough measurements, we can get rid of this random error or uncertainty. If we talk about absolute error, that's the distance, that's the difference between the value of your measurement and the accepted or published or theoretical value, right? So most of the time, we don't know the actual measurement, right, or the actual value. What we have is an accepted value, for instance. So for example, we say that the acceleration due to gravity is 9.8 meters per second squared. Well, that's only true around sea level, and it's not even true all the time then. But we're going to take that as the accepted value. So we'll take a whole bunch of measurements along at sea level, and then we'll average them together and we'll come up with this accepted value. So the accepted value of G is the magnitude is 9.8 meters per second squared. We also might have a theoretical value. So when we take a measurement in lab, we want to compare it to something. So sometimes we compare it to the theoretical value, sometimes we compare it to the accepted value, and go from there. So the absolute value is just the experimental value minus the accepted value. A lot of times we're only interested in the magnitude of these, right? So the magnitude of the absolute error. So if somebody told you that their error was about 3 centimeters, right? That's fine, but what we really would like to do is compare it to something. So for instance, if your error was 3 centimeters and you measured something a kilometer long, then you did pretty good, right? But if you were your measurement was 3 centimeters and you measured something only a meter long, that's pretty significant. So we talk about relative error. So the relative error is the experimental value, or the value you measured, minus the accepted value divided by the accepted value. And if we want the percent relative error, we multiply it by 100. Once again, normally we don't care if it's positive or negative, and we take the absolute value of the experimental value minus the accepted value. So for example, if our accepted value is 9.8 meters per second squared, and in one of your labs, you're going to measure G, and you found that it was 9.76 meters per second squared, then your absolute error is 9.76 minus 9.8, and we end up with minus 0.04 meters per second squared. Your relative error is 9.76 minus 9.8 divided by 9.8, and you end up with minus 0.0041. And if we want percent error, we'll just multiply it by 100, and we end up with an error of about negative 0.41%. Once again, most scientists are only interested in the magnitude of the relative error, so it will always be positive. We'll always take the absolute value of that. So you may have heard the words precision and accuracy, right? And here's the difference between those two words. Precision means the degree or consistency of reproducibility of a measurement. So 200 people measure the desktop and they all get the same, measurement. So the more precise the measurement, the less the difference between two observations of the same event. So this is just a rule of thumb, and your lab instructor may instruct you to do differently, but it's observed that most skilled observers can estimate readings to about 1/10 of the smallest division. So for example, let's say your smallest measurement is a centimeter, right? So let's say the smallest measurement on your meter stick is a centimeter. Usually it's a millimeter, and then the best you can hope for on an estimate is 1/10 of a centimeter or 1 millimeter. Okay, so most of the time, if you want to know about the precision, we'll take the uncertainty to be 1/10 of the smallest division. Once again, listen to your lab instructor, and sometimes we change this rule, and sometimes they have a very good reason for telling you to use something else. So this is the idea. Here's a measuring device, right? A ruler. And let's say we look at this measurement. Well, clearly this one looks like it's 3 centimeters long, right? And because it lands right on the mark. But what if it's here, right? So I don't know, it looks a little greater than 3.5, but it's definitely less than 4.0. So it actually is right in the middle, and we get 3.5. And most people could measure that pretty accurately. So let's look here. Here, it's not exactly, it's more than a half and it's less than 3, right? So it's more than 2.5 and less than 3. And what they did was a whole bunch of experiments looking at the errors measured by really good experimenters. And they said, well, you could easily divide it in half. And you could probably do a quarter. Well, they found is that really good researchers could do about 1/10 of this, right? So it looks like it comes out to be something like 2.8. So 1, 2, 3, 4, 5, 6, 7, 8, right? Plus or minus 1/10 of a centimeter. So if somebody asks you to measure something, you should say, well, I got 2.8 centimeters plus or minus 1/10 of a centimeter. Here's another example of measurements, right? Let's say the accepted value of a velocity that you measured in the lab is 3.2 meters per second, and your experimental value was 0.22. So the absolute value is the absolute error or absolute uncertainty is 3.22 minus 3.2, or 0.02 meters per second. The relative error is 3.22 minus 3.20 divided by 3.20, and it comes out to be 0.00625. And to get the percent error, we'll multiply it by 100, and we end up with less than 1% error. All right, now we want to talk about significant digits, right? So if we look at the significant digits, right, the first, and here's the rules, and we'll go over each one in a different slide, but the first significant figure in a measurement is the first digit other than 0, counting from left to right. And zeros to the left of the first non-zero digits are not significant, and zeros which occur between two significant digits are significant, and final zeros of the measurement containing decimal fractions are significant, and the number of significant digits are independent of the measuring unit. So, for example, let's look at these measurements. The first significant figures in the measurement is the first digit other than 0, counting from left to right. So in this case, this is the first significant digit, and here's the first significant digit. And here's a bunch of zeros, and the first non-zero number is the first significant digit. Zeros to the left of the first non-zero digit are not significant. So 0, 0, 0, they're not significant. This 0, not significant. These zeros, not significant. And this 0, not significant. So here are the significant digits in these numbers. So these zeros are not significant, not significant, not significant, and not significant. Zeros which occur between two significant digits are significant since they're part of the measurement. So for example, these zeros, these 3 zeros, not significant, not significant, not significant, and not significant. But these 2 zeros are significant. They're between two non-zero numbers, and the same for these 2. The final zeros in a measurement containing decimal fractions actually are significant. So here, if we list the number of significant digits, there's 3. Because what you're saying is that you know that the measurement is not 0.00401, right? You're saying that you know that for certain that these 2 are zeros. Okay, so here we have 3 significant digits. Here we actually have 6 significant digits, right? And 5 significant digits. And then 4 significant digits. And once again, this is significant. Then these zeros between these 2 numbers are significant. And any number and any zeros at the end of the number are also significant. The number of significant digits are independent of the measurement. So for instance, let's say you measured the measuring unit. So let's say you measure 10.6 centimeters, which by the way are 106 millimeters, which are 0.106 meters or 0.000106 kilometers. All 3 of these have three significant digits. So this 0 is significant because it's between 2 non-zero numbers. And there's 3 here. This first 0 is insignificant. There's still 3 here. And there's 3 here. We also want to round off significant figures. So I told you we want to stick to 2 decimal places in class, right? So let's say we want to round from 4 to 3 digits, right? If the last number is less than 5, we drop it. And if it's 5 or greater, we add 1. So for instance, here, we're going to go to 3 digits. So the 4 is less than 5. So we'll go to 4.42.5. And here we want to go from 4 to 2. Okay, so 8 is greater than 5, we add 1. 8 is greater than 5, we add 1. So if we wanted to round to two figures, we get 45. Here, we're going to round to 5, right? So in that case, 6 is greater than 5, we get 6. 6 is greater than 5, we add 1, right? And now we're at 67460. If we're going to add and subtract with significant digits, right, then we have to round off to the precision of the least precise measurement. What we're saying is this: you can't take a really good instrument that has lots of significant figures, right, and is really precise, okay, and then take another, like a meter stick, which is not very precise, right, and then add them together and get a better measurement. Like, it doesn't work that way. So you have to round off to the least precise measurement. So in this case, our least precise, so this has 5 significant figures, right? And 2 decimal places. This has 3 significant figures and 1 decimal place, right? So what we need to do is round this to 1 decimal place. So it becomes 331.5 plus 14.9, and we get 346.4. So if you're adding and subtracting, you have to round to the precision of the least precise measurement. So for example, here, once again, we have 1 decimal place, right? Okay, so we need to round this up. So what it actually becomes is 60 plus 15 is 75. All right, and one more example, right? if we have a velocity of 2.390 times 10 to the 10 squared, and this has 4.545609 times 10 squared, right? This has 3 decimal places, this has 4, so we have to round up to 3 decimal places and add. Same thing for temperature, right? Maybe this is a mercury thermometer that you're using, and this is a digital thermometer, right? So once again, we take the least significant and the least precise measurement, and we have to round this one to that. So multiplication and division with significant figures. So the number of significant figures in the result can be no greater than the number of significant figures in the measurement with the fewest significant figures. So what we have is 34.78 and 2.76767. So we go ahead and multiply them together, right? And when you put that into your calculator, you get 96.23626, right? And you're really precise here, right? You go out to the 5th decimal place. Well, no, you can't do that, right? We have to round up so that we have the same number of decimal places as the least significant figure, the least significant measurement, or the least precise measurement, which is the 34.78. So we'd have to round to 2 decimal places. So let's say we have something like this, a length, the width, and a height, and we need the volume. So maybe, for example, we're trying to find the density. Okay, so we multiply these 3 together, and we come up with 3.6 times 1 times 2.8, and we get 10.08. But all of these measurements only had 1 decimal place, so we have to round to 1 decimal place. And then the density, we'll find out in a couple of chapters, is equal to the mass divided by the volume. So we'll take our measurement, our mass, 20.23, and divide it by our volume, right? And then, once again, we'll need to round to 1 decimal place because our least precise measurement had 1 decimal place. So the number of significant figures in the result can be no greater than the number of significant figures in the measurement with the fewest significant figures. So we have 21.3, 9.80. We multiply these together to get an area. So this is the length and the width of a rectangle, for instance, right? And so what we're going to do is FOIL, right? So we'll multiply 21.3 times 9.8, 21.3 times 0.1, 0.2 times 9.8, and then 0.2 times 0.1. And then we'll add all the measurements together, right? And we'll come up with 2009 plus or minus 4 centimeters squared. So when you get into lab, you'll have to do this, right? You'll have to sometimes multiply or add measurements together with their uncertainties. By the way, if we take 12.71 and 7.46 and we multiply them together, we come up with 94.8 meters squared. Also, you probably are really familiar with this, but we'll talk about scientific notation, and we'll always write out something as a digit and then a decimal point and times 10 to the power of the measurement. So if we have a plus b, we note that this is 2 times 10 to the 5th plus 3 times 10 to the 5th, and we end up with 2.3 times 10 to the 5th, or 5 times 10 to the 5th. If we're multiplying, right, we'll get if we're adding, we get 1.75 plus 2.09 times 10 to the 4th, right? And what you want to do is change it so that they both have the same exponent for 10. So in that case, this becomes 0.29 times 10 to the 5th. And then we add 1.73 plus 0.29, and we end up with 2.02 times 10 to the 5th. However, our least precise measurement has only one digit to the left of the right of the decimal place. So we have to round to be as precise as the least precise measurement. When we're multiplying, what you do is multiply the numbers together and then add the exponents of the powers of 10. So in this example, we'll multiply 1.25 times 3.7, right? And then we'll add the exponents, and we get 10 to the 5th. And then we have to round to the least precise measurement. If we divide the numbers and we subtract their exponents. So once again, we talked about scalars and vectors. We said scalars have magnitude only, and vectors have magnitude and direction. The distance is a scalar, and it's the length of the total distance traveled. And displacement is a vector, and it's the distance between the final position and the initial position, and points from the initial position to the final position. If we're talking about one-dimensional motion, so for example, consider a really long train track that's perfectly straight. So there's no curves or anything. The train only has 2 ways it can go. It can go forwards or it can go backwards, right? So when we're talking about one-dimensional motion, where we're confined to move in a straight line, either along the x-axis or straight up and straight back down, right? Then the direction we can tell by saying is either positive or negative. So here's some example. If I move from x equals 0 to x equals 4, the distance I traveled is 4 meters. And the displacement is also 4 meters. It's 4 meters minus 0 meters, and it points in the direction from 0 to 4. So in this case, we're only moving in one dimension. We can either move forwards or backwards. So our displacement, sorry about that, our displacement is plus 4 meters. Let's say we make this trip, okay? So we start at 0 and we end up at negative 4. However, the distance we covered is 4 meters plus 4 meters plus 4 meters is 12 meters. However, our displacement is the final position, negative 4, minus the initial position. And so we end up with negative 4 meters. So the magnitude of the displacement is 4 meters, and the direction of the displacement is negative. Here's a better example. If you ever ran a marathon, you'll run about 26 miles. So the distance you cover is 26 miles. However, they usually put the start and the stop really close together, right? And there's let's say they're separated by about a quarter mile, right? And in fact, if we take positive x to be in this direction, our actual displacement is negative 0.25 miles. So the total distance was 26, but your total displacement from the beginning of the race till the end is only negative 0.25 miles. So displacement, we'll use a delta, that triangle, x, which is the final position in the x direction minus the initial position. And then we'll go on to define things like velocity. So the average velocity is just the displacement over time. So we get the average velocity will be x final minus x initial over t final minus t initial. X is measured in meters and t in seconds. So we end up with meters per second. So if you travel 300 miles in 6 hours, then your average velocity is 300 miles in 6 hours, or 50 miles per hour. Let's say you travel 6 meters in 3 seconds, and then 24 meters in 3 seconds. So you must have been going faster in that second part. Then you stop for 2 seconds, and then you travel 10 meters in 2 seconds. So the average velocity would be 6 meters plus 24 meters plus 0 meters plus 10 meters divided by 3 seconds plus 3 seconds plus 2 seconds plus 0 seconds. And we end up with 4 meters per second. This is what your trip would look like. So here, for the first 3 seconds, you get up to 6 meters. And for the second 3 seconds, you get up to 6 plus 24 meters or 30 meters. And then you stop for 2 seconds. So you stay at 30 meters per 2 seconds. And then you travel 10 meters. So you end up at 40 meters. So this was what it looked like. The velocity is delta x over delta t, which would just be the slope of this graph. So if we look at the slope of the first part of the trip, we get the velocity for the first part of the trip. Notice that here we're going faster and the slope, and the slope is greater. Here we're stopped and the slope is equal to 0 and the velocity is equal to 0. So if we look at the total trip, we end up with 4 meters per second, right, for an average velocity. However, if we look at the first part of the trip, we went 6 meters in 3 seconds, 2 meters per second. Then we went 24 meters for 3 seconds, which is 8 meters per second. Then we stopped, so the velocity was 0. And finally, we went 10 meters in 2 seconds, and we end up with 5 meters per second. Notice that these velocities are all different from 4 meters per second. So our average was 4 meters per second, but we were going really slow at first. Then we sped up, and then we weren't going so fast. We slowed down a little bit after we stopped. So this brings us up to an idea called instantaneous velocity. And what we'll do is look at shorter parts of the trip. So our instantaneous velocity here was 2 meters per second, and 8 meters per second, and 0 meters per second, and 5 meters per second. So if we look at just that part of the trip, that's what it would be equal to. And that's what we're taking up on Monday or next class. Thanks a lot.